So, we talked about relativity of simultaneity. If two events are simultaneous in one frame, they need not be simultaneous in other frame, and one may precede the other, and the ordering of event can itself be changed when you are changing the frame. But if you have two events at the same position, two different events at the same position, then the time interval between them from all frames from wherever you see is related by our time dilation formula. Improper and proper time interval depends on which you say delta t, which you say delta t prime. You can write both ways. The essential part is that the proper time interval will be the smallest. The frame in which the two events are at the same position, time interval measured from that frame will be smallest. So, depends on which you call delta t prime, which you call delta t. In this particular case, this is the proper time interval and this is the improper time interval. The essential thing that I want to convey is that if delta t is positive, then delta t prime is also positive. And if this delta is negative, delta t is negative, delta t prime is also negative. So, the ordering of event cannot be changed by changing the frames in such a case. So, if you have two events at the same position, the ordering is fixed once for all. If you have two events at different positions, one is here, one is here, one event is at x equal to x1, other is at x equal to x2, and this is at t equal to t1, this is at t equal to t2. So, one event is occurring earlier than the other, t1, t2 may be different. So, do I have a frame in which this ordering can be changed? Surely, if there is a frame, which is moving in such a way that at this time the frame is here and at this time the frame is here. So, if you have a frame which is moving this way and this frame is present at this event as well as at this event, and this velocity will be then x2 minus x1 by t2 minus t1. So, if you have this kind of a frame, in this frame the position of these two events will be same, and therefore, whatever is the ordering in this frame, that will remain the ordering from all other frames. So, if you can find a frame going with this velocity, then the ordering cannot change, and velocities which we can attain is less than or smaller than, less than or equal to c. For material things you cannot obtain velocity equal to c. So, if x2 minus x1 by t2 minus t1 is less than c, then yes, then we can always find a frame going at this velocity for which these two events will be at the same position, and therefore, the ordering in all frames will remain same. Such events can be connected by cause effect relation. There is a cause and then there is a effect. Apple breaks and apple falls on the ground, cause effect relation, that ordering cannot be changed. So, that is the message, but if this is greater than c, then you do not find a frame in which the two events are at the same position, and that is the case when the ordering is vulnerable, and change the frame and ordering can change. Now, today I will be talking of another beautiful phenomena, and that is synchronization. Synchronization of clocks. Because of this time dilation thing, if I look at a clock which is moving with respect to me, I am in frame S and I am looking at the clocks of S prime, or I am in S prime and I am looking at the clock of S. So, if a clock is moving with respect to me, then in my frame I will say that this moving clock is running slower. The speed of showing time, the rate at which the clock advances is slow. Moving clocks run slow, that we have done. Now, this is slightly different phenomena, that okay, I am here, suppose I am here, this is frame S and I am sitting here on in this frame, and then I am looking at clocks of S prime. This is S prime frame, and then there are clocks, let us say this clock at C1, this clock at C2, everything is moving this way. So, what I find from here, what I find from frame S about C1, I find that C1 is running at a slower rate, it is showing time, it is advancing, the clock is advancing at a slower rate. How much slower? By that same factor, square root 1 minus v square by c square. So, with respect to my clocks fixed in S, I say that with respect to these clocks, it is running slower at the factor with the factor square root 1 minus v square by c square. What do I say about C2? C2 is also running slower by the same factor as compared to the clocks in my frame. All the clocks of S prime are running slower than my clocks. On top of that, I will also find that these two clocks are not showing same reading at same time. That is, they are not synchronized. Synchronized means two clocks are synchronized. So, if I have a clock in my drawing room, if I have a clock in my bedroom, and I say that okay, both the clocks are synchronized, I can use this clock or that clock to decide when I have to go for the office. At the time this is showing 800, at the same time the other clock is also showing 800, even if it is at some distance. That is the meaning of clocks are synchronized. So, what this S observer finds is, this is running slow all right, this is running slow all right, they are running at the same rate which is slower than this. At the same time they are not even synchronized. One clock is showing more time than the other clock at the same instant. At the same instant I look at this clock, at the same instant I look at this clock, and I find that one clock is showing more time, one clock is showing less time. That is called lack of synchronization, it is not synchronized. So, let us see how it works. So, suppose at time t, S observer or observers note the readings on clocks C1 and C2. See that these are two events. These are two events. At time t, this clock is here, I am talking from S frame, this clock is here at this x, this clock is here, its position is here given by these coordinates, and the observer which is here notes the time shown on the clock C1, and this observer who is opposite this clock notes the time shown on this clock C2. Now, these are two events. So, let us analyze these two events. E1, S observer, there are several observers. So, some observer, S observer, some observer, because these events are occurring at different places. So, the legal mechanism has to be devised to look at these two at the same instant. So, one possibility is that this observer is ready, this observer is ready, and when the clock comes to him, he measures the time here, when the clock comes to him, he measures the time here, and they have already decided that at a particular instant t, he will see which clock is opposite him and measure time here, and this person will at the same instant, they have already decided that at the same instant this person will look at the clock reading whichever clock is in front of him. So, event 1 is that this observer notes the reading of this C1. And similarly, E2 is once again S observer, maybe a different observer, notes the reading. This is C1 and this is C2. From S frame, what are the coordinates? Where did the event occur and when did the event occur? So, from S frame, the first event occurred at, say, x is equal to x1 here x is equal to x1, and at time t is this t. Event E2 that occurred here, x is equal to x2, so x is equal to x2, and at the same time, at the same instant, they are looking at C1 and C2. What is the time in of these two events in frame S prime? So, we can use Lorentz transformation, and for E1 we can write T1 prime is equal to T minus x1 v by c square and then divided by square root 1 minus v square by c square, and for E2 we can write T2 prime is equal to T minus x2 v by c square square root 1 minus v square by c square. And so, T2 prime minus T1 prime is equal to minus v by c square, you can take common, x2 minus x1 and divided by square root 1 minus v square by c square. So, you see that T1 prime is not equal to T2 prime, and T1 prime and T2 prime are the time observed noted by these as prime observers of these two events E1 and E2. So, these are also the clock readings, that is the meaning of clock, the clock is meant for that. So, whatever is the time of event at a particular location, the clock there must show that time, that is why the clock is there, and hence the clock reading here is T1 prime, the clock reading here is T2 prime, and S observer notes that okay, this clock is showing T1 prime, although the time is T, but this clock is showing T1 prime, that is perfect. And this observer says okay, the time is T, but it is showing T2 prime, and the fact is that at the same instant these two clocks are showing two different times, T2 prime and T1 prime, and this is the difference. And since in this picture x2 is more and x1 is less, so this is positive, x2 minus x1 is positive, then because of this minus, this thing is negative, and that means T2 prime is smaller than T1 prime. So, this clock here is showing a smaller time and this clock here is showing a larger time at the same instant t. So, for S frame, this C1 clock is ahead of C2 for all time, they are not synchronized, and the rule we will formulate that since the clocks are going towards right, this is the rear clock and this is the front clock. So, the rear clock is ahead of front clock, so it is opposite. In the motion for this translation, this is the front and this is rear, this is ahead and this is behind. But for showing the time on the dial, it's other way, this is ahead and this is behind. So we say that the rear clock leads and the front clock lags. By how much? Here is the difference, and you can see what is x2 minus x1. x2 minus x1 is the separation between the clocks as measured from the frame S, and in S frame these clocks are moving. So x2 minus x1 is the separation between these moving clocks, which should be less than the rest separation between these clocks. So from S prime, if I ask, from S prime, what is the separation between C1 and C2? That is the rest separation. And from S1, I see that separation is x2 minus x1, that is the moving separation, moving length. And moving length is less and rest length is more, and the factor is once again that square root 1 minus v square by c square. So if you look at this factor here and this expression x2 minus x1, which is the moving length, and you divide it by square root 1 minus v square by c square, its value increases and becomes the rest length between these two clocks. So if this you write as rest length L, then the difference between the two times shown in C1 and C2 will be written as the difference L V by C square, where L is the rest separation. Between the clocks, C1 and C2. Okay. So remember this final result. If you have two clocks which are moving with respect to yourself, parallel to the line joining the clocks, then the one which is at rear will be showing more time, the one at the front will be showing less time, and the difference of time will be the rest separation between the clocks multiplied by the speed of these clocks and divided by c square, L into V by c square. So that is the lack of synchronization. The next topic I will take is transformation of velocities or addition of velocities. If you have two frames and you look at some object from this frame and the other frame, then how these two velocities and the frame velocity, they are related, that is under transformation of velocities. So Galilean transformation we know very well. If I have two frames S prime and there is some object, then the velocity of the object with respect to S, velocity of the object with respect to S prime, and velocity of S prime with respect to S, just vector addition, simple. But in Galilean transformation, the things are reasonably okay for low velocities only. For high velocities, we have to bring in Lorentz transformation, and then let us see how the velocities transform. So, velocity addition. Or velocity transformation. So, I have a frame S, I have a frame S prime, as usual. This S prime is moving in positive x direction with respect to S, time t equal to t prime equal to 0 when the origins cross all those standard conventions. And then there is a particle, let us say there is a particle here P, and at time t the coordinates are x, y, z at time t. This is an event, the particle is here at time t, this is an event. So, as seen from S, for this event the position is x, y, z and the time is t. And as time t elapses, dt time elapses, t becomes t plus dt, the particle moves, and when the particle moves and goes somewhere else, then the coordinates become x plus dx, y plus dy, z plus dz at time t plus dt. And then we say that ux, x component of the velocity, is dx dt, y component of velocity is dy dt, and z component of velocity is dz dt. This is the definition. And same definition applies for S prime also. The same two events, this event P is here and then this event P is here. The description, if you ask from S prime, where did the event occur? There will be some position described by x prime, y prime, z prime. At what time P was here? That will be t prime. This event here, where did the event occur? So, S prime description will be x prime plus dx prime and so on. And when did it occur? T prime plus dt prime. And similarly, the definitions will be this dx prime divided by this dt prime will be ux prime. Uy prime is dy prime dt prime and uz prime is dz prime dt prime. And what we want to do, we want to write expressions for ux prime, uy prime, uz prime in terms of ux, uy, uz and the velocity v of the frame. So, we can start from Lorentz transformation equations for position. X prime is equal to x minus vt and then divided by square root 1 minus v square by c square. And from here you can write what is dx prime. I can, since this v is constant, it is the frame velocity, as time passes this v does not change. So, I can write this as x minus vt times gamma. Gamma is independent of time, gamma does not change with time. So, dx prime you can write, dx prime will be dx and minus v dt times gamma. Similarly, start for time, you have t prime is equal to t minus x v by c square multiplied by gamma, and therefore you can write what is dt prime. Dt prime will be equal to dt and minus dx v by c square. So, dx v by c square and times gamma. We have expressions for dx prime and we have expressions for dt prime, and we start from x prime is equal to x minus v t square root 1 minus v square by c square, and this factor we are writing gamma, which is independent of time, and therefore dx prime is this and dt prime is this. Now let us calculate what is this ux prime. So ux prime, which is dx prime dt prime, is equal to, here is dx prime, dx minus v dt times gamma. So dx minus v dt gamma, and here is dt prime, dt minus v dx over c square and times gamma. So cancel these two gamma first and divide numerator and denominator by dt. So what do you get? This is equal to dx dt minus v, this dt cancels out, we are dividing by dt. So dx dt minus v, and denominator also you have to divide by dt. So here it will become 1 and minus this v, and then this is dx dt, c square and dx dt, and this is dx dt is ux, dx dt is ux, so ux and minus v and divided by 1 minus this is ux v ux by c square. So that is one rule, ux prime is equal to ux minus v divided by 1 minus v ux by c square. In Galilean transformation you have ux prime is equal to ux minus v. So this is the new factor which is coming in. So you have this relation, remember this, we will be collecting these things. So this is one equation that we have obtained, ux prime is equal to this. What about uy prime, component of velocity in y direction? The position is same, y prime is equal to y. So y prime is equal to y, and therefore dy prime is equal to dy, but uy prime is not equal to uy, because uy prime is dy prime dt prime, uy prime is dy prime dt prime. So dy prime is this, but dt prime is not dt, dt prime we have written here, dt prime is here, dt and minus dx v by c square gamma. So this is dt and minus dx times v, or you can write v dx divide into gamma. This is dt prime, this is dt prime, dt minus v dx by c square times gamma. So uy prime is equal to dy prime dt prime, that is the definition of uy prime. In y direction, how much is the displacement? From y it has gone to y plus dy. So this dy dt is uy, component of velocity in y direction. So you have uy prime is dy prime dt prime, and that is equal to dy and divided by dt prime, that is dt minus v dx times gamma. And this is equal to, again divide by dt in numerator and denominator. So you get dy dt here, and this becomes 1, and dx dt becomes ux. So v into ux by c square also. Dt prime is dt minus v dx by c square. So, it is this, and gamma here, okay, gamma here, and 1 by gamma will be square root of 1 minus v square by c square. So, I can write that factor here, 1 minus v square by c square. So, the expression for y component of velocity in S prime looks more complicated than the x component here. The denominator is same, but here it is dy dt into 1 minus v square by c square. So, you have uy prime is equal to, this is uy, dy dt is uy. So, uy into square root 1 minus v square by c square and divided by 1 minus v ux and by c square. And of course, I do not have to do anything for uz prime, you know what it will be. Uz prime will be similar expression. Okay, so, we can collect these things here. Ux prime is equal to ux minus v by 1 plus v ux by c square, not 1 plus, 1 minus. This first equation I have written. Then uy prime is equal to uy square root 1 minus v square by c square divided by the same expression 1 minus v ux by c square, and uz prime is equal to uz and square root 1 minus v square by c square divided by 1 minus v ux by c square. So, these are velocity transformation formula, Lorentz transformation for velocity transformation. So, these are the equations, Lorentz transformation equations for velocities as you change from S to S prime. If you change from S prime to S, only thing you have to do is change primed quantities to unprimed and unprimed to primed and put minus v in place of v. So, you get that inverse transformation from there. So, if you have to write the inverse transformation, very simple, only thing you have to do is you in place of ux prime you write ux, and in place of ux you write ux prime, and minus v becomes plus v, and in denominator 1 and minus v becomes plus v. So, it is plus v ux by c square, and similarly here uy is equal to uy prime square root 1 minus v square by c square divided by 1 minus v ux by c square. Remember, in transformation of y component of velocity, you are also using ux, x component of the velocity of the particle. So, that also should be noted, and similarly uz will be uz prime square root 1 minus v square by c square 1 plus v ux by c square. So, these are the inverse transformation equations. If you know the velocities in S prime, velocity of a particle in S prime, you can write the velocity of that particle in S prime. Okay, so we will stop here.